So, for those of you who are here, welcome to this tutorial on work. So, we are going to look at two problems and try to solve them, which will hopefully give you an idea of how these problems can be approached. So, the first one is here. So, we have a piston cylinder arrangement. You can of course pause and read the question for yourself. So, we have a gas in a frictionless piston cylinder mechanism. So, it says frictionless, which means that there are no losses, which makes it possible for us to use our usual equations and processes. We do not have to worry about friction forces and so on. It is at an initial pressure of 1 bar. Okay. So, I am going to mark that I have initially a pressure of 1 bar here. The diameter of the piston is 10 centimeters. Okay. I am going to convert it to meters. So, that is 0.1 meter. It rests on stops. So, there are these stops here and the piston is resting on it initially. The question says that the piston weight is such that it requires a pressure of 1.5 bar to be lifted from the stops. So, the atmospheric pressure outside is 1 bar. The piston itself has some weight. Because of both of these, the piston is resting on the stop and it cannot move up unless the pressure here becomes 1.5 bar. So, that is something I understand from this. It says the gas is now heated, which causes the piston to rise slowly. So, we are giving some amount of heat to this gas. We will see that we usually represent this as Q. So, we are giving some amount of heat. So, what I would expect is, as this heat is given here, the temperature of the gas increases, the pressure of the gas also increases. At some point of time, because the pressure is high enough, higher than whatever is the pressure on top and the weight of this piston is going to move up. So, that is something we see. So, this causes the piston to rise slowly. What it says is, after a rise of 10 centimeters, it touches a spring. So, what I understand from this is that this gap is 10 centimeters. And the spring has a stiffness of 10 Newton per meter. That is 10 into 10 power 3 Newton, sorry, that was initially per millimeter. So, that in Newton per meter, that is 10 power 4. The heating of the gas is stopped when the spring is compressed by 1 centimeter. So, what I see is that this gas here, initially this is a 10 centimeters away, and then after it touches the spring, the process is done till the spring is compressed by 1 centimeter or 0.01 meter. We are asked to find out the work interaction for the gas, the piston, the spring and the atmosphere, and we are also asked to sketch these processes on a PV diagram and show the work interactions by hatching the appropriate areas. So, we have more or less all the information which is given initially, which is plotted over here. So, you may want to start thinking about it. Okay. So, we are now going to see how we can approach this problem. So, what we see is that the gas needs a pressure of 1.5 bar in order for it to push this piston up. So, maybe let us start looking at what this would look like on a PV diagram. So, we can find out what is the initial volume of this gas. I am going to call that as V1. So, the initial volume of this gas is given as the cylindrical area of the cylinder. So, that is pi d square by 4 into the initial height. So, we have the diameter as 0.1 meter and the initial height is 25 centimeters, which is 0.25 meter, and this will give us some answer in meter cube. So, this is the initial state. So, the pressure initially was given as 1 bar inside here. So, I can actually plot this. I have a pressure value of 1 bar, let us say this corresponds to 1 bar. I have a volume corresponding to whatever this is, I can calculate it out. So, that is our state 1. Now, I am going to give heat to this gas and the pressure is increasing from 1 bar. What we see is this piston can only move when the pressure inside becomes 1.5 bar. So, initially the pressure is 1 bar and then the pressure is going up to 1.5 bar. During that process the piston is not moving. So, pressure is going from 1 bar to a second pressure of 1.5 bar. During this process the piston is not moving, which means that the volume is constant. So, I can now plot my second point. So, I am going from a pressure of 1 bar to a pressure of 1.5 bar. During this process the volume is unchanged. So, the volume is constant. So, that means it must be a vertical line. So, going from 1 bar up to 1.5 bar and this is my point 2. So, we now reach this point, sorry, we are still here, we are still at this point, but the pressure has now gone up. So, after this what we see is that the piston can move 10 centimeters till it hits the spring. So, once it has started to move, it gets away from the stops and it starts to move up. Now, the volume will start increasing as it moves up, but the question is what about the pressure inside? So, the piston is being moved up against the atmosphere, which is a constant pressure, and against this gas is pushing the piston against the mass of the piston, which is also constant. So, what we see is once the piston starts to move, it is going to move against the atmospheric pressure, which is constant, and against the weight of the piston, which is also constant. So, the piston is going to move at constant pressure until it reaches this point, which corresponds to 10 centimeters. So, let me find out what would be the volume at that point. So, the volume over there, so the pressure at that case is going to be equal to the pressure at 2. The volume at that point is going to be whatever was the volume before, which is equal to V1. So, volume is constant. So, V2 is equal to V1 plus whatever is this gap. So, that volume is pi d square by 4 into 0.1 meter. I can find out what this value would be. So, this is the volume in meter cube. So, this is now going to be a constant pressure process. So, we are going from this point at a constant pressure till we reach the volume of V3. So, that is our point 3. This is V1 or V2 and we reach the point 3. So, when we reach this point V3, what happens is that we are touching the spring, and after that we are still continuing to give heat. So, the pressure is going to increase and we are still continuing this process until we deform the spring by a distance of 1 centimeter or 0.01 meter. So, what we see is we can find out what is V4. It is essentially V3 plus whatever is the volume when we go up by 1 centimeter, and we can find out this value, and the pressure is going to be higher because we are now doing work against the spring, we are pushing the spring. So, the question is what is the pressure at that point 4. So, we have V4 which is fairly nearby and we have some pressure corresponding to 4. Now, we know that this is a spring we are considering this to be a linear spring, which means the force is proportional to the deformation of the spring. Since the area of cross section of the cylinder is constant, it means also that the force is proportional to the volume displaced, which means on a PV diagram this is going to look linear after this. So, I can find out what is the constant, but it is going to look linear like this, and what I am going to get finally is some 0.4 such that this corresponds to this V4. So, this is how the entire process looks like on a PV diagram. I need to find out the value at 4, which I can because I know the spring constant. So, the force in the spring is essentially K into N, spring constant in times not N, I am calling it, let me call it as some X, K into X, this is the force, and if I divide by area I get pressure. This is pressure due to the deformation of the spring, and I have to add this to whatever is already the pressure, which at which this will move, which is 1.5 bar. So, that would be the pressure at 0.4. So, X is 0.01 meter, K is known, it is I think given as 10 power 4 Newton per meter, and area is pi d square by 4. So, that gives me, let me just separate this out, P plus 1.5 bar is my P4. So, I can find out this in pascals, and now what I want to do is to find out the work done. So, what we see is this is 1 bar which represents atmospheric pressure. So, whatever is the work done against atmospheric pressure would be in general given as P atmosphere, because it is a constant. Okay, against atmosphere, if we look at whatever is work done, this is work against constant pressure. So, P atmosphere into the final volume minus the initial volume would represent work which is being done against the atmosphere. If I take the pressure due to the weight of this piston and calculate what is the work done, okay, that would be the equivalent of finding out mgh, that would be work interaction due to the piston. If I find out half kx square and find out corresponding pressure and volume work, that would be the work interaction due to the spring, and all of these put together is the work interaction with respect to the gas, because sum of all of them should be 0, some are positive, some are negative, and this should be able to give us this. Okay. So, I can find out this in many ways. One way is to find it out graphically. So, if I want to find out the work interaction for the gas, it is the area under this curve, essentially this area. So, I can graphically find out this area. This is a rectangle, this is also a rectangle, this is a triangle. I can sum them up and find out the area, and that would give me the work in joules, or I can take each of them separately and find out. So, for example, work interaction for the atmosphere is this rectangle, work interaction for the piston is this rectangle, sorry I mean this rectangle here, this rectangle, and work interaction for the spring is this little triangle on top. So, I can find them out individually and sum them up. That is also another way I could find out these values. So, I would encourage you to find out these values. What I will do is post the numbers in the forum once you have tried this out and ask me what the values are.